Welcome! Integration. So today we're going to review integration, and I'll teach you a few things that you possibly haven't learned to do with integration as well. Okay, so definition: an antiderivative or integral of a function f of x is a function uppercase f of x such that f dash, the first derivative of uppercase f of x, is lowercase f of x. The indefinite integral of f of x is the set of all functions uppercase f of x such that f dash of x is lowercase f of x. And we denote this with this symbol, the integral of f of x dx. And we add an arbitrary constant c to show an indefinite integral because, remember, when you differentiate a constant, you get zero, right? So there are infinitely many possible functions that are the antiderivative of a given function. All right, so we have several rules of integration which make this process a bit easier. If c is a constant, then the integral of the constant times f of x is the constant times the integral. The integral of a sum is the sum of the integrals, just as for differentiation. Some important integrals to remember are: if n is not equal to -1, then the integral of x to the power of n dx is 1 over n plus 1 x to the power of n plus 1 and then plus c. But if n is equal to -1, then the integral of x to the -1 dx, or the integral of 1 on x, is the natural logarithm of x and then plus c, where c, of course, is any particular constant, or any given constant. Okay, the integral of e to the power of x dx is e to the power of x and then plus c. The integral of sine of x is minus cos of x. Now remember, the derivative of cos of x is minus sine, so the derivative of minus cos of x is sine of x. All right, so in a sense, we're going backwards from differentiation. The integral of cos of x is sine of x plus c. The integral of cos to the -2, or 1 on cos squared of x, is tan x plus c. Okay, so we have a few rules, just like we do for integration, or for differentiation, sorry. So integration by parts. Here is the formula for it. The integral of u dv is equal to the product of u and v minus the integral of v du. So I'll show you an example of this pretty soon. A definite integral, or Riemann integral, denoted with a number there and a number there, the bottom and the top. It's defined as the limit of the sum of the f of x subscript j times the change in x. So that limit as the number of intervals goes to infinite. So basically, if you have something like a function something like this, here's your a, here's your b, and then this is the x-axis, say. Okay, so if you are calculating the area under that curve between a and b, well, then you could break this up into rectangles whose height is the value of the function, say, on the right-hand side, and you could sum up the areas of those rectangles. And then this is one method that we use to numerically estimate area under the curve, or the indefinite integral from a to b. For example, if you remember, we have the trapezoidal rule and Simpson's rule and other kinds of quadrature. Okay, so as these little delta x, the width of these, tend to 0, that's the number of those tending to infinite, the number of those rectangles, and hence you would get the area under the curve when the width of these rectangles goes down to 0. Okay, so that is the definition of this definite integral. Okay, and so we write the integral from a to b is equal to So what we do is we integrate this, and then we sub in b, we sub in a, and we take a difference. So this is equal to f of b minus f of a, where f of x is the integral, or any given integral, of lowercase f of x with respect to x. All right, example. Let's calculate the indefinite integral, not the definite one, the indefinite one up here, of x squared plus 3x. So integral x squared plus 3x dx equals. So now what I do, since this is just a polynomial, I'm using this rule. I'm adding 1 to the exponent, and then I'm dividing by that new exponent. So 2 plus 1 is 3. So we have x cubed, and then I divide by that. So I put a 1/3 in front. And then the same for this. So this is 3 times x to the power of 2 divided by that new exponent. Makes that over 2. And then don't forget the plus c. So where c is any real number. Provided that we're taking these as real functions. So if we were taking those more generally, then c would be any complex number. Okay, let's have a look at example 1.11. So this is an integration by parts question, but I'll remind you of that formula. So where was it? Integration by parts is right here. Let's just write here u dv. The integral of u dv is uv minus the integral of v du. So that's our integration by parts formula. So now we have the integral of the natural log, and I just write log, but you can write ln if you want to. So now I want to identify, looking at this, a u and a v. All right, so natural log of x, let's call that u, and v, let's call that x. Okay, so then given that, I can write my formula here. So I've got v is x and u is log x. So we've got x for v and then log x for u, and then subtract the integral of the other way around, which is v first and then du. So that's d log x. Okay, I'll put a bracket around that. Now usually you would see a dx there, right? But we're not finished with this because we can make a substitution. So this part's done. That's just x, natural log of x. And then this is derivative of log x with respect to x. And then this whole thing integrated with respect to x. Now remember, I told you earlier that the reason I like to use Leibniz's symbols is because of the aid to memory via fractions and, other algebra. So you look at this and you think, okay, if these were fractions, if this were a fraction, then I would be able to cancel the dx with this dx, and it would look exactly like this. So that tells me that this formula here that I've used is correct. So, but what is it? By substitution. Okay, now let's simplify this. So we know that the derivative of log of x is 1 on x. So therefore, we have the integral of log of x with respect to x is x log x minus x times 1 on x dx. And now look, you can cancel the x, and so we've got x log x minus the integral of 1 dx, and the integral of 1 dx is just x, so we have x log x minus x, and then don't forget the plus c. Okay, so we can factorize this if we like. So let's go ahead and do that. We can pull an x out and say that this is x times log x minus 1 and then plus c. All right. Now, in the tutorials, I'm pretty sure we will do other examples, but if we don't, remind me and we'll do some. Okay, example 1.12, calculate the integral of this fraction. So what we want to do is recognize a relationship here. So have a look at that denominator. If I differentiate that denominator, x squared minus 3x plus 5, then I get the numerator. So I get 2x minus 3. So that tells you then that this is going to work out nicely by substitution, and that we should let u be equal to that denominator, x squared minus 3x plus 5. Okay, now let's differentiate. So du on dx is equal to 2x minus 3. Now you see that's the numerator, but the substitution that we're going to do later would require substituting these, right, and then replacing the dx in terms of du. So I like to do that right here, but I don't put equals. I just say what I'm going to substitute. And so what I'm doing to get this, though, is I'm rearranging this as if this is a fraction, right? But we know it's not a fraction. So what we have then is dx will get replaced by du over 2x minus 3. Okay, and so then the integral of 2x minus 3 on u, because that denominator is u, okay, dx is equal to the integral of 2x minus 3 over u. Now we were going to replace dx with this, and we knew that from algebraically rearranging this, pretending that that is a fraction. Okay, so that's how we got it, but that's just aid to memory. So what we say here after we've done that is that we did so via substitution. Okay, so we have this now, and you can see that these two are identical, so we can cancel those, but we'll say by substitution. Okay, now having canceled those, we get the integral of 1 on u du, which is just log of u plus c, but we know that u is this. So subbing that in, we've got natural log of x squared minus 3x plus 5 and then plus c. All right, and this is our integral of 2x minus 3 over x squared minus 3x plus 5 dx. Okay, next page. So these are getting progressively more tricky. So if you need more practice of this, then I strongly recommend that you pick up Stuart and find the appropriate section on integration and find some practice problems and do a whole bunch, hopefully checking your work along the way. Okay, so the next integral we have is the integral of 1 over the square root of 1 minus x squared. Now, for this, what you want to happen here is you want to choose a substitution for x so that that inside the square root becomes a square, and then you can take the square root of a square, getting the thing inside, right? So, inspired by that, what you want to happen, remember that, so note cos squared theta plus sine squared theta is equal to 1. Okay, and so then 1 minus, so cos squared theta then is 1 minus sine squared theta, and so cos of theta is the square root of 1 minus sine theta when cos theta is positive. Okay, so we want to use that because you see this looks like the denominator there. So inspired by these identities here, what we want to do is say let, and so you can treat this as scratch paper if you like, this little corner. So let x be equal to sine of theta. Okay, so given that, we know this will work out nicely because this looks like that. So we want to differentiate x with respect to theta. And so the derivative of sine of theta with respect to theta is cos of theta. So then in our substitution, we'll be substituting dx, replacing that with cos theta d theta. Okay, so let's go ahead and do this. So we have integral of the square root of 1 minus x squared dx equals, now making the substitution, we have this, but then replacing the dx with cos theta d theta. Started to write dx, but let's do it all there. Okay, so now it's all in terms of theta. So this one, remember, we simplified that to say that that's cos of theta in the denominator. So we have integral of 1 over cos theta, then d theta. Cancel those, and we have the integral of 1 d theta. Okay, so you can see then that that is just theta plus c, but we don't want this in terms of thetas, we want this in terms of x. Okay then, so x is the inverse function of sine of theta. So in other words, that's arcsine or sine inverse, which on the calculator is sine superscript minus 1, but here I write arc sine. So arc sine of x plus c. And note that arc sine of x is sine superscript minus 1 x. Now that does not mean not 1 on sine of x. This means inverse function, right? And that's why I write arcsine, because so you don't accidentally confuse it with this one, right? You don't want to confuse it with 1 on sine. Okay, so we have arcsine x plus c. Now, you might want to know where that's valid. So let's briefly consider sine of x and its inverse function, that is. So we'll go ahead and plot by hand sine of x up until it fails the horizontal line test. So from, let's see, from pi on 2 radians minus pi on 2 radians, it goes something like this. Okay, so this is sine of x. Now let's draw a dashed line for the line y equals x. Okay, because, and then this incidentally is y equals 1, and down here got y equals minus 1. Okay, so the reason why I drew this dashed line at y equals x is because the inverse function would take this and reflect it about the line y equals x, and so you could sketch the inverse function in that way. Okay, so we'll say arc sine of x is the reflection of sine of x about the line y equals x. Okay, now the reason I haven't drawn this beyond pi on 2 radians and minus pi on 2 radians is because the sine function comes down here, right? And if you were to take the part where it comes down again and reflect that about the line y equals x, you would no longer have a function because it would not pass the vertical line test. Okay, so you have to stop here when you do that. Now, can I reflect this successfully by hand? Okay, I think I'm going to get the computer to do this. So what I'm going to do is plot sine of x as x goes from minus pi on 2 to pi on 2. Okay, so there we go. We have something like what I've drawn here. All right, but let's also draw, so put this in brackets. I'll put x for the line y equals x. Okay, so there, that's the orange line, the line y equals x. And then after that, actually let's put an aspect ratio . Okay. And so after that, let's also plot the inverse function arc sine of x, and that's the one in green. All right, so hang on a moment. I'm going to get a red pen if I can find one. All right, I've got a red pen. I don't know if it works. So here I'm going to draw the inverse function carefully, right? It's a bit tricky. And then it comes down something like this. Okay, now you can see here that it goes between -1 and 1. So where can we put this? Well, I need a little bit more space. You probably do too. Let's just put it in here. I'll put it in a little box. So arc sine of x is less than or equal to 1, but greater or equal to -1. Okay, and there's the plot of it on the left, but here's a hand drawing of that as well. All right, great. So we have our integral. Did we add c? Well, we didn't finish this off. No, we did. It's right here. Yeah, plus c. Yes. So maybe box this off because that's our answer. Okay, moving on. So this is getting a little bit trickier here. I'm trying to show you a variety of different examples that you may or may not have done before, just so you're properly prepared. Okay, so calculate the integral of 1 over the square root of 1 plus x squared dx. Now here again we need a trig substitution. And if you really don't know what substitution to make, look, you can get a little hint from Mathematica here. So I'll just write integrate 1 over sqrt 1 plus x squared with respect to x. Okay, it gives me arc shine. That's pronounced shine, arc shine. Okay, so this tells me that it would suggest that I take a trig substitution replacing x with shine of x. So I'll show you how that goes, right? And so you see I've used this to get a hint here, right? But when you do enough of these, you get so good that you can just remember which trig substitutions will work out, but also the form inside that square root inspires what you should do too. And I'll show you what I mean. So we let x equal to sine h, so it's like sin and then a h, but pronounced shine. Okay, so it looks like sine for a reason. It's called the hyperbolic sine function. So this is 1/2 e to the power of theta minus e to the minus theta. Right, so that's the exponential e, 2.718281828, and so on. And here I can just calculate that. So let's just n exp 1.0. Okay, and then after that I will press enter to show you what that is. 2.718281828459045, and so on. All right, so with this, we can easily differentiate that now because we know what the derivative of e to the theta is with respect to theta. So taking derivatives, dx on d theta is the derivative with respect to theta of 1/2 e to the theta minus e to the minus theta. Okay, we pull the theta out. The derivative of e to the theta with respect to theta is e to the theta. The derivative of e to the minus theta with respect to theta is minus e to the theta, but there's already a minus sign there. So what we end up with is 1/2 e to the theta plus e to the minus theta. Now this is called cosh, hyperbolic cosine function. So remember I said it wasn't a coincidence that that starts with sin, and it's also not a coincidence that this starts with cos. Okay, because the derivative of a sine is cos, likewise the derivative of shine is cosh, and the derivative of cosh is shine. Right, so there's no extra minus, like for example the derivative of cos of theta is minus sine of theta, but the derivative of cosh of theta is shine of theta. All right, now we've got another identity, so we'll say note cosh squared of theta. So when we square cosh, we have 1/4 e to the theta squared, which is e to the 2 theta, and then twice the product of those, so plus 2 times e to the theta times e to the minus theta, and then plus e to the minus 2 theta. Okay, now e to the theta times e to the minus theta is 1, so this middle term here is 2, so we've got 1/4 e to the 2 theta plus e to the minus 2 theta, and then 2/4 is 1/2. Okay, now let's take shine and square it. And so shine squared is the square of this, so we've got 1/4 e to the 2 theta. Now this time there's a minus there, so it's minus 2 e to the theta times e to the minus theta, and then plus e to the minus 2 theta. Simplifying this, we've got 1/4 e to the 2 theta. Now that's minus 2 because e to the theta times e to the minus theta is 1. But we'll take that outside the bracket, and so minus 2/4 is minus 1/2. So we've got e to the minus 2 theta and then minus 1/2. Okay, now notice these two are quite similar. There's a plus 1/2 here, there's a minus 1/2 here, but the rest is the same. So if we take cosh squared minus shine squared, these vanish, and we have 1/2 minus minus 1/2, which is 1. So cosh squared theta minus shine squared theta is equal to 1. All right, now put in a little box here. Uppercase x squared minus y squared equals 1 is a hyperbola. So that's why we call these two hyperbolic functions. All right, so given this identity, then we want to use that in relation to this, you see. So cosh squared theta is equal to 1 plus sine squared theta. Okay, so taking square roots, cosh of theta is equal to the square root of 1 plus sine squared theta. Okay, and now that looks like that denominator. So that tells us why we took that substitution. All right, now we got a derivative of x being cosh. So in our substitution, we're going to replace dx with cosh theta d theta. Okay, so let's do our integral now. Now, making the substitution, we have the integral of, so x is sine of theta, but 1 plus x squared square root will become cosh of theta. So we've got 1 over cosh of theta. And then replacing dx, getting this from that derivative calculation, dx gets replaced with cosh theta d theta, and magically we can cancel those cosh thetas. So what we get then is the integral of 1 d theta, which of course is just theta plus c. Okay, so we've got theta plus c, but now theta is the inverse function of x equals sine of theta. So this is arc sine of x plus c. All right, now since theta has exponentials in it, as theta increases, x keeps going too, right? There's no upper bound on that. So there's no upper bound on the input here, right, for this one. This is valid for all real x. Okay, and we've got our integral done. So let's move on to the next page. So fundamental theorem of calculus states that if f of x is continuous over the interval from a to b, closed interval, so for all x between a and b inclusive, if it's continuous in that region, then the integral of f of x, or the definite integral of f of x between a and b, is uppercase f of b minus uppercase f of a, where uppercase f is an antiderivative of f of x. So in other words, the derivative of uppercase f of x is lowercase f of x. All right, so given that, let's use the fundamental theorem of calculus to find f dash of t and show that it's increasing when t is greater or equal to 0. All right, so this is f. Let's see, what is that? Yeah, so f is defined as the definite integral. Now that's integrating with respect to x, but then in the bounds of integration, we have a t cubed. So that is in fact a function of t. All right, so let's go ahead and do this. So now what we have, f dash of t is equal to, right, by the fundamental theorem of calculus, it's f of t cubed minus f of 0 multiplied by the derivative of t cubed with respect to t. So we need the chain rule here, so this involves the chain rule. All right, now if there were only an ordinary t there, then we would just have this being f, uppercase f of t right there, right? But we've got a t cubed, so we actually have to use the chain rule as well. Okay, so uppercase f of t. So what we have then, this is just the function inside. according to the fundamental theorem of calculus. So that is 1 minus e to the minus 2, and we sub in t cubed, and then we square it, and then we subtract the same thing when we replace x by 0. So 1 minus e to the 0, and then we've got to multiply this by the derivative of t cubed. So that is 3t squared. Okay, now let's simplify. So the square of t cubed is t to the power of 6. And over here, e to the 0 is 1, so this is 1 minus 1, which is 0. So we have 1 minus e to the minus 2t to the 6th, and then multiplied by 3t squared, and we can write that on the left-hand side. Okay, so here's our derivative. Now, if you don't believe me, let's go ahead and calculate. So here, up here, I have entered a function. So f as a function of t is the integral of this, as x goes from 0 to t cubed, all right? So I've entered that as a function, then I'll display it, and then I'll differentiate it. So Mathematica here has calculated what that is, and it's related it to what we call the error function. Now, the error function is used in probability and statistics. Okay, and so it's related to this. It's an integral of a negative power, or e to the minus x squared. Okay, so I'll leave it at that. So it's related that to the error function, and then I've taken this and differentiated it, and yes, it recognizes it as this. So if I then factorize that, okay, we have this, but it's actually this, right?